Good morning. George Notchik here. Today is August 22nd, 2018. This is the first of the three-part series that will be covering the Coriolis effect. The first part is going to be a review of the mechanics of motion. There'll be some mathematics here, but it won't be too deep. Most people should be able to grasp and understand the mathematics in this particular module. Part 2 is we'll be getting into the Coriolis effect. It will be a conceptual rather than an analytical treatment and discussion with a minimal amount of math, some algebra. Part 3 will be a rigorous treatment of the Coriolis effect with vectors, cross products, rotating and non-rotating coordinate systems and reference frames, which will then give us exact values for the Coriolis forces. We'll be using some differential calculus. In this module, I'm going to be discussing the laws of motion based on Newtonian mechanics. All objects and frames of reference will be of low enough velocity so that we do not have to take into account relativistic effects. Now, what do we mean by low enough velocity? Well, in Einstein's special relativity theory, all the equations involve what we call the Lorentz Factor, which has this form. It's the square root of 1 minus the ratio of v over c squared, where c is the speed of light in the medium in which we are considering our problem, and v is the velocity of a reference frame or an object within the reference frame. C, speed of light in a vacuum, has the value of 300 million meters per second. In the English system, it's 186,000 miles per second. And if you're involving short enough times, the value I like to use in small time intervals is 11.8 inches per nanosecond. Nanosecond is a billionth of a second. So in 1 nanosecond, light travels about 1 foot, 11.8 inches. It's very, very fast. The time that it takes an electromagnetic signal, an RF plane wave, or a laser light to go from the Earth to the Moon and back, make that trip, it does it in about 2.5 seconds. So speed of light is extremely fast. Now, I'm going to look at what does the velocity of an object have to be, how little does that velocity need to be compared to the speed of light so that the Newtonian mechanics deviates less than 1/10 of a part per million from the special relativity theory. So what we're going to do is we can look at this and write it as 1 minus delta, where delta is approximately 1/2 v over c squared. Now, if the velocity is near zero or at zero, the Lorentz factor is 1, and our deviation is 0. So when v over c is extremely small, the Lorentz factor becomes unity, and Einstein's special relativity equations reduce to the Newtonian equation. So there's no difference between the Newtonian mechanics and special relativity theory. So as velocity approaches the speed of light, we have a correction factor, and there becomes a great deviation between Newtonian mechanics and the relativity theory, special relativity theory. But if the velocities are sufficiently small, the results from the the special relativity theory become identical for all practical purposes with the Newtonian mechanics. And we know that to be true because we've had very successful results using Newtonian mechanics for space flight, launching satellites, trips to the moon and back. Newtonian mechanics is perfectly fine. Well, let's first see is what we want to do is we want to have our delta, the deviation, to be less than 0.1 part per million. That is 1 out of 10 million. Well, if you put the numbers in, you will find that our velocity has to be less than the speed of light divided by 2,236, which is 83.4 miles per second, or 300,000 miles per hour. Okay. Well, we don't have any technology that can get us this fast right now here on Earth. 83 miles per second. That's extremely fast. We can achieve these types of velocities when we get down to subatomic particles, particle acceleration down in the quantum mechanical world. But in dealing with macroscopic objects like you and I, baseballs, marbles, basketballs, things like this, what we call macroscopic objects where we have a sufficient amount of mass, there isn't any way we can approach these velocities on the Earth. So the requirement, the speed requirement for the Newtonian mechanics to agree to within 1/10 of a part per million with the special relativity theory is easily met here on Earth with macroscopic objects. That is to say that for speeds below 83.4 miles per second, that the Newtonian mechanics is going to be accurate to better than 7 significant figures at velocities that are usually encountered by humans. And in fact, if, say, the velocity of an object is 300 kilometers per hour, which is around 187 miles per hour, then the Lorentz Factor and Newtonian mechanics agrees with the special relativity theory to around 13, 14 decimal places. So for all practical purposes, there's no difference between the Newtonian mechanics and special relativity theory when we're dealing with these low velocities that we normally encounter here on the surface of the Earth. So we do not need to take into account relativistic effects. The first law states that unless an object is acted upon by some outside or what we call an external force, then an object at rest will remain at rest, and an object in motion will remain in motion at a constant velocity moving in a straight line. What this means is, suppose you have an object. It's sitting on the ground. The first law tells us it's going to sit there forever unless we push on it with some force or some other force like a wind force imparts its energy to it to move that object. If there is no force acting on that object, it's going to sit there forever. And the same thing, if the object is in motion, if it's traveling through space or say rolling on the floor, if there's no external forces acting on it, it's going to continue rolling at a constant velocity in a straight line that it initially started with. Now, the only way for it to deviate from that is if there's some sort of an external force that acts on this object. And if there's an external force that pushes on this object, then of course the object's going to deviate away from a straight line. That's what the first law tells us. As long as there's no net external force acting on an object, it will either remain at rest if it was initially at rest, or it will continue going at a constant velocity in a straight line forever and ever until there's some force acting on that object. So that's what we mean by the first law. Now, the second law, normally people encounter the second law expressed as F equals ma, where F is a force acting on an object, m is the mass of the object, and a is an acceleration that the object undergoes when a force is applied. Now, this is not how Newton originally stated it. This is a simplified statement of Newton's second law. Newton stated this law in more general terms. He expressed it using the calculus that he had invented, and the accurate description of the second law is force, which is a vector, it has a direction and a magnitude, is equal to the time rate of change of momentum with respect to time. That's what this symbology means, is this is a change in momentum over a change of time. And momentum, our vector p, we designate as momentum, is an object's mass times its velocity. And velocity in general has direction and magnitude. That's what the bars on top designate. These are vectors. So if we look at the way Newton stated this, force then will be the time derivative of momentum with time, or rate of change of momentum with time. So we put in for momentum mv with respect to time, and those that know calculus will know that we can expand this out. This will be mass times the time derivative of velocity with time plus velocity times the time derivative of mass with time. Now, in treatment of Newtonian mechanics, most of the situations that we encounter never have the mass of an object changing with time. So the mass, the change of mass with respect to time goes to zero. So this part of the equation drops out. And we also know that the time rate of change of velocity, we define that as acceleration. So putting in for here, we get mass times acceleration, which is the form most of you always see Newton's second law expressed as. But the more exact equation has a second term that we neglect because mass does not change with time in most of the situations that we deal with. However, we cannot neglect this second term in rocket science. You have to include it, because what happens when, say, we launch a rocket? Well, as a rocket burns its fuel up to project it up into space, the mass of the object is changing. The mass of the rocket system is changing because it's burning up its fuel. It's losing mass. We have a rocket, say we're launching it, and we have some fuel tanks on the side, and as this rocket is launched, we're burning fuel. We have, say, 3 engines, and we have fuel in here, and some in the rocket. And as that rocket goes up, the fuel depletes, it's losing mass, and so force equals mass dv dt plus v dm dt. This is changing with time. This is getting less and less and less, so we have to include it in the equation. And in fact, once the tanks have emptied out, the fuel tanks drop away, they get jettisoned, and we end up with a step function in the time derivative of mass. So, in certain situations like rocket science and dealing with rocket propulsion, we have to use a more exact form of Newton's second law. Now, let's talk about motion, types of motion. Now, in general, we have two types of motion. We have one type called translation. This is where an object moves in a straight line path. There's no curving. It's a straight path. We call that translation. Then there is rotation, where an object moves in a circular path. Now, there's a special case of translation that we call an inertial reference frame. An inertial reference frame has no accelerations. Pure translation at a constant velocity is what we call an inertial reference frame. Translation in general could have an object changing its velocity with time as it goes in a straight line. It could say start slow and then speed up and then slow down. As long as it's going in a straight line, we call that translation. But if we put a further restriction on it, where the object moves in that straight line always at a constant velocity, we call that an inertial reference frame. No accelerations. Now, in rotation, an object is moving in a circular path. Say this is our object. It has some mass, m, and it moves in a circular path at a constant distance from the center of the circle. R never changes. It stays at the same value all the time for the object going around in the circular path. Now, we describe how the object moves around this circular path by its angular velocity. We designate it omega. This is called angular velocity. And angular velocity is just the time rate of change of the angle with time. If I say designate a reference point, say this horizontal line is my reference point, then if I measure from this reference datum an angle, say theta, to the vector or the line from the center of the circle to the object, that angle we call theta, and omega is the time rate of change of the angle with respect to time. We have change of angle over change of time, and that gives us the rate at which the angle changes with time. We call that angular velocity. Now, there's another velocity that we can describe this movement by, and we call it the tangential velocity. That is the linear velocity of the object tangent to the circle. Now, this velocity, this tangential velocity, which I designate vt, is related to the angular velocity. Vt, the tangential velocity, is just the angular velocity omega times the radius of the circle that the object is tracing out in its circular path. Now, the units on omega is just revolutions per unit time. And we use units for revolutions that they're in radian measure. There are 2 pi radians in 1 revolution. And we use seconds as time. I should say, in general, that's not right. it's radians, angular measure in radians per second. Or we could also put it in terms of degrees per second. Many of you are more familiar with degrees. Well, there's a relationship between radians and degrees, is that there are 2 pi radians around the circle, and everybody knows that there's also 360 degrees around a circle. So we can say divide through by 2 is that we have pi radians in 180 degrees. This is the conversion factor. If someone gives you the angle in degrees, you divide by 180, multiply by pi to get radians. If you have radian measure, divide by pi, multiply by 180 to get the degrees. Now, this is the tangential velocity. It's linearly related to the angular velocity through the radius. The larger the circle for a given angular velocity, if we hold the angular velocity constant and we change the radius, the tangential velocity has to be larger. You can see that. Suppose I have a circle, a larger circle around here, and we extend our radial vector out. You can see that if these 2 angular measures, say we have a stick sitting out here, and we look at an object at the center of the stick and then one at the end of the stick, as that stick rotates, the velocity tangent at the middle is 1/2 the velocity that it'll be out here. So the tangential velocity depends on the radius. The larger the radius for a given angular velocity, the larger the tangential velocity. Now, there's another parameter that we want to talk about, and that's accelerations, the centripetal acceleration. Now, with our object moving around a circle, we said we have a velocity that we can attach to it that's tangent to the circle. We call it the tangential velocity, and again, our omega is the angular velocity. Now, associated with this is an acceleration, which we call the centripetal acceleration. I'll designate it AC, and it's directed towards the center of the radial direction of the circle. We call this our radius of curvature, and it's directed towards the center of the radius of curvature. And the acceleration, centripetal acceleration, is related to omega and r as omega squared r, which is also the tangential velocity squared divided by r. And you can see that here. If I put in for Vt omega r squared divided by r, I have omega squared r squared over r, which is omega squared r. So these are the relationships. The magnitude of the centripetal acceleration is the angular velocity squared times the distance out, or the tangential velocity squared divided by the radius. Now, what this tells us is that if we have some angular velocity omega, the acceleration experienced by this object as it's going around in circular motion is directly dependent on the radius. If we go twice as far out, we have twice the acceleration. And it goes as a square. If we double the angular velocity, the acceleration quadruples, or goes up as a square. Yeah, it's quadruple, twice the original twice the original angular velocity squared, so we end up with 4 times the acceleration that we started with. Now, if omega, the angular velocity, and the radius are constant, we call this uniform circular motion. That is, the tangential velocity is the same everywhere along the circular path. It never changes. It has a constant magnitude because omega is constant, the radius is constant. So uniform circular motion means the angular velocity remains the same. It's like a record on an old turntable or a CD disc playing. It's always rotating at a constant angular velocity, or the same amount of revolutions per second. That's what we mean by omega being constant. Now, if the angular velocity and the radius are constant, and if we remember that acceleration is a time rate of change of velocity with time, we might see that there's a problem here. Because if velocity is omega r, and we put it into this, take the time rate of change with time, omega is constant, r is constant, so omega r is constant, so there is no change with time, and we would think that this equals 0, that there can't be any centripetal acceleration. These are what we call scalar equations. That's true for a scalar equation, but there's something else going on here. This is not equal to 0 if we keep in mind that velocity is just not a scalar quantity. It's a vector quantity, and so is acceleration. Velocities have both magnitude and direction. Even though the velocity might have a constant magnitude as it traces out the circle, its direction is continually changing. At this point, it's pointing upwards. At this point, it's pointing straight over to the left. At this point, it's pointing downwards. So the velocity vector is always changing direction with time, and that's what gives rise to the acceleration. I'll just quickly show this for people that are of interest. Don't let this scare you. For those of you that aren't real comfortable with trigonometry and algebra, you don't have to worry about not understanding what I'm doing here. It won't affect what we're going to be discussing later on. Now, suppose I use the horizontal line as a datum, as a reference point. And this, if I draw a line from the center of the circle to the object at some point on the circle, at some time it might be there, then this angular measure we call theta. Okay, it's the angular measure from our datum, our horizontal datum, to a radial line that connects the object to the center of the object, of the circle. We call that theta. Well, omega is a time derivative of angular measure with respect to time. It's the amount that this angular measure changes with time. That's what we mean by omega. Now, that's a scalar. This is not a vector quantity. This is what we call a scalar. It has no direction associated with it. It's just a rotational velocity, how many revolutions per second. Now, the radial vector, r, going from the center to the object, I'll call this vector r. And if I use Cartesian coordinates, this is the ax direction. That's what I have here. And this is the ay direction, the xy directions. And I can break this radial vector into components. I have a vertical component, which is r times the sine of theta, the magnitude of this vector, times the sine of theta, and its horizontal component is r times the cosine of theta. So I can write r as being r times the cosine of theta in the ax direction plus sine theta in the ay direction. Now, if I take the time derivative of r, the time derivative, or the rate of change of r with time, the radial vector, it has both a magnitude and direction. Here's our magnitude, here's our direction information. This gives us velocity, tangential velocity vector. So if I do this, remember, r is a constant with respect to time. This radial distance never changes with time. So that comes out. And the time derivative of this, the theta is changing with time. So if I take the derivative, I end up with minus sine theta in the ax plus cosine theta in the ay. And then we have d theta dt. Well, what is d theta dt? It's omega. From here, the time rate of change of angle with time, I can replace that with omega. So this is omega r. So the magnitude of the tangential velocity is omega r. That's what we had before. Remember, bt is omega r. That's the magnitude of the vector. This magnitude is 1. Now, if I take a second rate of change with time, that is, I take the rate of change of velocity with time, and remember, we call this acceleration, the centripetal acceleration. Well, what is that? Well, omega and r are constant, so they remain out. And if I take the time derivative of this, minus sine becomes minus cosine theta in the ax, and time derivative of cosine theta with ay on ay with respect to times become minus sine theta in the ay direction. Well, what is this? Well, this, compared to this is just minus. This is the opposite direction of the radial vector. We could write this as minus omega r times cosine theta ax plus sine theta ay. And this is a unit vector in the radial direction. And we can write this as r with a unit vector ar directed outward. If our ar vector is this way, as a position vector, then the centripetal acceleration is in the opposite direction. It's directed this way, which I have here. This is the direction of our centripetal acceleration. And then I also have a d theta dt here. Well, what's d theta dt? Well, d theta dt again is omega. So if we look at this, this becomes omega r times omega, or omega squared r, in the minus ar direction. So that's our magnitude of our centripetal acceleration. So AC is omega squared r, as we had before. So that's where it arises. Even though the angular velocity, omega, and the radial distance out, the radius of the circle that an object traces in uniform circular motion, even though those are constant, we get rise to an acceleration because the direction of the tangential velocity is changing with time, and it's because the vectors change position and orientation with time that gives rise to the acceleration, not the radial magnitude or the angular momentum. It's because the direction of velocity is constantly changing. That's what gives rise to the acceleration. And this is a problem that I'm going to deal with later that I call Ute acceleration. There's a fella that seems to think that the value of velocity in this direction, and if we go halfway around the circle and take the velocity in this direction, subtract them off, that it gives rise to some new acceleration, but it isn't. What it is an approximation to the centripetal acceleration. I'll be showing that in another video later on. Okay, now, since we now know the relationship with centripetal acceleration to the angular velocity in the radius, we have centripetal acceleration is omega squared r. And remember, from Newton's equation, force equals mass times acceleration. Well, if we put in for a centripetal acceleration, we have mass omega squared r, and this is a force that's acting on an object to hold it in uniform circular motion. We just multiplied the centripetal acceleration by the mass. This is the centripetal acceleration. And we can get the amount of force that's acting on that object to hold it in uniform circular motion. Now, physicists like to use what are called force diagrams or body diagrams. When objects do not move from position, we call that statics. And if they deviate in direction and change velocities, we call that dynamics. Now, if the sum of the forces acting on an object is equal to 0, there can't be any acceleration of that object because of Newton's second law. Remember, force equals mass times acceleration? Well, if the force is 0, the mass of an object is not 0, so the only thing left on this side of the equation is A. So, if the forces are 0, then there can be no acceleration of the object. The object has to remain going in a constant speed in the same direction. That's the first law. This statement here is basically Newton's first law. We get this from the second law. This is the second law. Force equals mass times acceleration. And if the forces are 0 acting on an object, there's no outside forces acting on that object, then the acceleration is 0. The object can't deviate in its path. This is the first law. And what do we mean by accelerations? Well, accelerations is a time rate of change of velocity with time. So if A is 0, there is no time rate of change of velocity with time. The velocity has to be constant. If velocity is constant, then the time rate of change of velocity with time, when v is constant, is 0. That's what we mean by no outside external forces acting on an object. Now, if the object is going around in uniform circular motion, we have a force acting on that object directed to the center of the circle. We call this the centripetal force. I designate it as Fc. Now, since physicists like to have force diagrams, and if an object is not deviating, then we like to say that the sum of the forces are 0. So we introduce what we call a fictitious force. It's not a real force. We put it in there so that the body diagrams indicate that some of the forces are 0. And the centrifugal force, I designate CF. It's opposite and in the same magnitude as the centripetal force. So these forces balance out, so the object will not either fly outward radial out or nor will it go inward in a radial direction if there is an equal and opposite centrifugal force acting in opposition to the centripetal force. And that's why we call this centrifugal force a fictitious force. It's not really there acting on the object, but you feel it. Yeah, you might think, well, I feel it if I'm on the merry-go-round. Well, no, what you're really feeling is the centrifugal force. And say if you're standing on a roundabout or a merry-go-round, the friction at your feet is holding you on that roundabout as it's turning. There's a centrifugal force acting inward, but that's balanced out by the frictional force holding you to the roundabout. The force is balanced so you don't move away. But if the roundabout starts spinning too fast, then the frictional forces can't hold you and you get thrown out. Now, in general, remember we were talking about translational and rotational motions. Well, in general, in space and in a plane, we can have combinations of translational and rotational forces, and we call this curvilinear. Shoot, it's wet. We call this curvilinear motion. It's a combination of translation and rotation. So for example, if you have an object, say tracing out some sort of a path, this is what we call curvilinear motion. Now we can break curvilinear motions up into two components, a translation and a rotation at any given point. At this point, if the object is here, it has a centripetal acceleration directed towards what we call the radius of curvature. You can think of this being, there being a circle here. At this point, a circle of a given radius can describe the motion as this object is passing by. And say in this part where it's straightening out, we have pure translation, and then over here we have again some more rotational motion, and we have a centripetal acceleration directed in that direction towards the center of curvature. And then if we go out further, the object can just have pure translation going in a straight line. So in general, curvilinear motion can be broken down into two components, and by a property that we call superposition, which is true in linear systems, or it's a definition also of a linear system, we can solve a problem, break it into two parts, into components, analyze it in terms of rotational motion at a point and the translational motion, and then combine them to give us the overall net motion of the object. This is what we typically do with problems because superposition property holds for motion in plane, on a plane, and in space. Now, this is only true for linear systems. You can't use this sort of thing in general, say, where relationships are not linear. Well, what type of relationship do we not have linear relationships? That's, well, when we're talking about kinetic energy. You might remember kinetic energy is 1/2 mass times the velocity squared. So, with respect to the velocity, we don't have a linear system. We can't combine kinetic energies in general when we have different velocities because of the squared factor. Superposition doesn't hold. Now, there is one case where it does hold, is if you look at the motion, say, of an object in translation, and we have a velocity, a net velocity, we can break it into components. We have a velocity in the x component in the x direction. We have a velocity component in the y direction. Well, remember, kinetic energy is 1/2 mv squared. So if I look at the kinetic energies in the horizontal and vertical components, what do we have in the horizontal? It's 1/2 mvx squared. In the y, it's 1/2 vy squared. And if I combine them to get the net kinetic energy by using the Pythagoras theorem, remember, this side squared plus this side squared gives me this side squared. So if I define kinetic energy total in the hypotenuse of the triangle, I have 1/2 mvx squared plus 1/2 mvy squared. I pull out the 1/2 m's, and I've got Vx squared plus Vy squared, and lo and behold, what is that? That is V squared. So 1/2 mv squared. So in this case, it does work out that the energies acting in the horizontal and the vertical directions can be combined to give us the overall kinetic energy of an object. Now, let's put some numbers in for the Earth. These are numbers that we're going to be using for the Coriolis effect, and you'll need to remember them, but we'll derive them here now and use them in part. Okay, now we're going to look at and get some numbers for the Earth. The Earth is rotating about its axis at 1 revolution per day. The radius of the Earth, from the center of the Earth out to the equator, has a mean value of 6,371 kilometers. Here we're looking at the Earth from the top down, from the North Pole. Here's the North Pole, and the edge is the equator. Now, at the equator, we can attach a tangential velocity of an object sitting at the equator. It's going to be rotating around on the Earth with the surface of the Earth, and we can attach to it a tangential velocity. The Earth, again, has an angular velocity of a revolution per day. There's 2 pi radians in a full circle in a revolution, and a day is 86,400 seconds. So this works out to 2 pi divided by 86,400 is 72.7 times 10 to the minus 6 radians per second, or 72.7 microradians per second, which is, remember, there's pi radians in 180 degrees. You use that conversion, you get 4.16 millidegrees per second, and that works out to 15 arc seconds per second. So the Earth, anyone sitting at the equator, moves about 15 arc seconds per second, or 1 revolution per day. Now, let's look at the tangential velocity of an object sitting on the equator. Well, remember, tangential velocity is omega r. So we have the angular velocity of the Earth times the radius of the Earth at the equator. So 72.7 times 10 to the minus 6 radians per second times 6,371 kilometers gives us 0.463 kilometers per second. Converting to miles per hour is 1,666 kilometers per hour, and that works out in the English system to 1,036 miles per hour. An easy conversion factor from kilometers to an easy way to convert between kilometers and miles, or miles to kilometers, is to remember that there are 5/8 times kilometers. You take how many kilometers you have, multiply by 5/8, and that gives you miles. Or going the other way, if you take miles and multiply by 8/5, that will give you the number of kilometers. The exact number is that there is 1.60934 kilometers in 1 mile. But 8/5 is 1.667, so it's pretty close to the number. You have a little bit of error, but it's not too great. It's roughly 5 out of 160. So about 4% error is what you'll get using this conversion factor. So for quick and dirty, just use 5/8 to go back and forth. Now, we have a tangential velocity at the equator of 1,036 miles per hour in the English system. Now, this is only at the equator. as you move at higher latitudes, you're moving up along the surface of the Earth. See, this is the center. Here's the north. This is the axis of the Earth. We have the North Pole sitting here. That's this point. And here's our equator. So here is the radius of the Earth from the center of the Earth out to the equator. Now, to get it at some latitude, if you're up here at some latitude, let's call it theta L, which is our latitude angle. At the equator, we're at 0 degrees latitude, and at the North Pole, we're at 90 degrees latitude. So what we use is what we want to find is this radial line here, this distance to use for our radius. So to get the tangential velocity of an object, say, out here, inward towards the North Pole. Remember, the Earth is spinning around this way, so the tangential velocity is going into the board. So that tangential velocity, Vt, will just be the angular velocity of the Earth times the latitude radius. I will call this RL. That's the latitude radius, and it's related to the radius of the Earth at the equator by the cosine of theta L. So when theta L, we're at 0 latitude, cosine of 0 is 1, we get this value. Up at the North Pole, theta L is 90 degrees, cosine of 90 is 0, so there is no tangential velocity for someone sitting on the Earth at the North Pole. If you're sitting on the North Pole, you're just going to spin around like this. You'll have no tangential component. You just rotate if you're sitting on the pole. But you get off the pole a little bit, then, for example, I'll be going around the pole, say 1 foot away from the pole, and I have a tangential velocity. And that tangential velocity grows as I get further away from the pole. Keep this in mind. This is very important for the Coriolis effect. As you get further away from the center of rotation, your tangential velocity increases for a platform that's rotating at a uniform, constant angular velocity. The further you get away from the center, the faster, the higher the speed of your tangential velocity becomes. Now, just as a sideline here, let's look at the number, let's look at the centripetal acceleration that something sitting on the equator experiences. We want to find the centripetal acceleration. Well, remember that centripetal acceleration is omega squared r. So at the equator, the centripetal acceleration will be omega squared of the Earth times the radius of the Earth at the equator. Well, if you put in the numbers, if you have 72.7 times 10 to the minus 6 radians per second squared, you have to watch your units. These have to be in radians per second for the omega, and we multiply by the radius of the Earth, 6371 times, we have to put it in meters, so we have to multiply this by 1,000. Put that in here to get us meters, to go from kilometers to meters. And this value works out to, if you put it into your calculator, you're going to get 0.0336 meters per second squared. That's the centripetal acceleration that an object sitting on the equator, on the surface of the Earth, experiences. Let's compare it to the gravitational acceleration. Well, gravitational acceleration at the equator is 9.82 meters per second squared. Let's ratio them. Let's look at how does the centripetal acceleration for someone sitting on the equator compare to the gravitational acceleration that he experiences? The gravitational acceleration is what's responsible for giving you your weight when you stand on a scale. So if I take g and divide by the centripetal acceleration, we have 9.82 divided by 0.0336, and this works out to 292. That tells us that the gravitational acceleration is 292 times larger than this centripetal acceleration that you're going to feel that's trying to throw you off the Earth. Well, for a 150-pound man, for that force that you're experiencing on a scale at the equator, the force that you're going to feel tending to throw you off the surface of the Earth, the centrifugal force, remember, is equal to the centripetal force. So the centrifugal force is going to be equal to the centripetal force, and that is 150 pounds for a 150-pound man divided by 292, or roughly 300, and this works out to 1/2 of a pound force. So you're going to be lighter at the equator by about 1/2 pound. A 150-pound man is going to be lighter at the equator by 1/2 pound than he will be at the pole where there isn't any centrifugal force. Remember, you're sitting here, there's going to be a centrifugal force that's tending to throw you off the Earth, but up here there is no centrifugal force. You just sit and spin around, rotating. There is no tangential velocity, no centripetal acceleration that you feel. So you have no centrifugal force trying to pull you off the Earth. But at the equator, you have a centrifugal force on a 150-pound man that amounts to about 1/2 pound force trying to pull you off the Earth. That's why you don't feel the Earth spinning. There's hardly any force acting on you to tend to throw you off the Earth, even though at the equator the velocity, tangential velocity, is 1,036 miles per hour. And the reason for that is the size of the Earth. The fact that the radius of the Earth is 6,371 kilometers gives rise to the fact that you have very little centrifugal force trying to throw you off the Earth. Because remember, the centripetal acceleration is Vt squared over r, and as r gets larger and larger, the centripetal acceleration gets less and less and less. And the Earth being so large makes the centripetal acceleration so small you don't feel it. Now I'm going to solve a very simple motions problem to show you how easy it is to find the trajectory of an object. Now, let's look at the flight of a ball thrown from the surface of the Earth. For purposes of this discussion, we can assume that we are on a flat plane because we're dealing with distances less than, several miles. You're going to throw a ball, you're lucky if you're going to get it, what's the furthest anyone can throw, maybe 300 feet or so. So, if you take a small portion of the surface of the Earth where you only have a mile distance out, it's indistinguishable from a flat plane. So we can, for purposes, assume we are on a flat plane with very little error. We call this linearization. Now, the forces acting on a ball thrown, we're assuming that we're throwing a ball, say, at a 60-degree angle upward at a velocity of 80 kilometers per hour, which works out to about 50 miles per hour at a 60-degree angle. We want to know how far out will it go before it hits the Earth? How much time does it take to reach the peak of its trajectory? And how high does it go? Call y at TP. How high up does it go? Now, on the Earth being so large, when we're dealing with areas on the order of, a few miles, the gravitational force fields are essentially parallel. Actually, the force field is directed towards the center of the Earth, but these deviate so little over a distance of a few miles, and most definitely in hundreds of feet. It deviates so little from being parallel that we can consider it to be parallel. The difference is if you have a parallel force field pulling on an object, then the trajectory of that object when it's in ballistic flight, I call it free flight, the technical term used currently these days is ballistic flight. And ballistic flight is flight that only has the force of gravity acting on it. There's no other forces acting on an object in ballistic flight or free flight. I will now use the term ballistic flight. I was using free flight before, but they're interchangeable. I learned it when I took physics. We called it free flight. People are now calling it ballistic flight. Now, in ballistic flight, with only the force of gravity acting on an object as it sails through the atmosphere, through the air of the atmosphere, if the force is all parallel everywhere along the flight trajectory, the path traced out by that object will be a parabola. And a parabola is symmetric. That is, it'll go up, it'll reach a max height, and it'll go back down in the same manner that it went up, and the velocity that it hits the ground will be the same velocity as it was thrown up with. Now, if we have much larger distances, technically speaking, this is not a parabola. It's an ellipse. But it collapses to a parabola when the force field is parallel. If the force field is what we call a central force, where all the lines of force are directed to a same spot, like at the center of the sphere, we call that a central force field, and the trajectory is an ellipse. When you're dealing with space mechanics, where you're going out hundreds of miles, this approximation no longer works because the lines of force are no longer parallel in that situation. But for this situation, we can make this approximation with extremely little error. There's no error indistinguishable from between the elliptical orbit and the parabolic orbit when you're dealing with distances of miles, and certainly in less than a mile. Now, so we're going to ask, how far does it travel? How much time does it take to reach the top of its trajectory? And how high does it go? Now, first we need to do is we have to understand that in ballistic flight, the horizontal and vertical components act independently of one another. Key point, that the horizontal component of velocity does not interact with the vertical component of velocity. Very important concept here, which this means that if I throw a ball up at 80 kilometers per hour, the horizontal component never changes. The velocity in the horizontal component always remains constant with its initial value. There's nothing in the horizontal direction to change it. There's no force acting on it. Remember Newton's first law. An object in motion tends to stay in motion unless acted upon by an outside force. The only force acting on the object is in the vertical direction, and that is the gravitational force field. The gravitational force field is perpendicular or orthogonal to the horizontal component. It has no influence on the horizontal component whatsoever. but it does influence the vertical component, and we make use of that fact. So we first break our initial velocity into components, horizontal and vertical component. We have, if we have 80 kilometers per hour at a 60-degree angle, then the vertical component is 69.3 kilometers per hour, which works out to 19.25 meters per second. This is our V initial in the y direction. And in the horizontal component, the horizontal direction, 80 kilometers per hour. In the horizontal direction, the component is 40 kilometers per hour, which works out to 11.1 meters per second. And this is the initial velocity in the x direction. Now, everywhere along here, there's going to be a horizontal and vertical component. The vertical component magnitude changes, but the horizontal component always remains the same at this value. This never changes. The only component that changes is in the vertical, and that is due to the gravitational force field. Okay, how about to find the time that it takes to reach the maximum height? Well, what happens? We throw the ball, it goes up, it's slowing down, and then it reaches the top. There's no vertical component to the velocity at this point. At this point, it's neither going up nor down. It's just going straight horizontally. So there's no vertical component. The y component to the velocity is 0. So we set the equation, the time to reach maximum height, is we take our initial velocity in the y direction and we subtract off acceleration times time. Remember, velocity is a time derivative of acceleration with time, or we can just call it acceleration over time. So if we multiply, I'm sorry, other way around. I thought that looked wrong. That acceleration is a time derivative of velocity with time. So we can say this is velocity per unit time. So the velocity is just acceleration times time. We make use of that fact. So the acceleration, the only acceleration acting on this object is gravitational acceleration, our little g. Remember, little g is 9.82 meters per second squared on the surface of the Earth. So we have our initial velocity in the y direction, and that component's getting smaller and smaller because of the gravitational acceleration pulling, force of gravity pulling it down. So we take this gravitational acceleration times the time to the peak. This is our overall velocity, and we set that equal to 0 because there is no y component of the velocity at the peak, at the top. Solve for TP. TP is V initial in the y direction divided by g. So our initial velocity in the y direction is 6.9, or we got to use meters per second, not kilometers. We got to do everything in the MKS system now, meters and seconds. So we have 19.25 meters per second, and we divide by 9.82 meters per second squared. So this comes out in seconds, and this value is 1.96 seconds. So the time to get to the top of our trajectory is 1.92 seconds when we throw the ball at 80 kilometers per hour at an angle of 60 degrees. Now, how about the height to reach the top? Now that we know how much time it takes to get to the top of the trajectory, we can calculate how high up it is when it reaches the peak. Generally speaking, any distance up from the ground anywhere along this trajectory We'll call this distance y. Our y is the initial height plus 1/2 the acceleration times time. Well, in this case, we have no initial height. We're sitting down at the ground, so our y0 goes to 0. And our height at any point along this trajectory is just 1/2 times the gravitational acceleration t squared. I need a square in there. Now, so y at tp then is we just put in for time the time at the peak, and that gives us the overall height. So putting in our numbers, 1/2, 9.82 meters per second squared, times time to the peak squared, 1.96 squared seconds. Seconds squared go out with the seconds squared. We end up with meters, and this value is 18.86 meters, which is about 63 feet. So the object will reach a height of 63 feet or 18.86 meters. Now, how far out does the object go when it hits the ground? How far is it from the initial throw? Well, this being symmetric, remember, as I told you, we have a parabola here. So the distance here is the same as the distance here. So if it takes time tp, time to the peak, to get to the center, then it's twice that to get to where it hits the Earth. So the time final, the time it takes, or the flight time of the object, is just twice the time it takes to get to the peak. Right? Let's put in our numbers. Now, the key point here, remember, is that the gravitational forces, gravitational acceleration, does not affect the horizontal component of the flight. So everywhere along here, the x component of the velocity is equal to the initial component, which was 40 kilometers per second, or 11.1 meters per second. That's the initial velocity in the x direction, and it maintains that velocity through the whole flight in the x component. So to find how far out it goes, all we have to do is take the x component towards the time, times the time. So the distance will be just twice the time to the peak times the initial x velocity. So this is twice 1.96 seconds times the initial velocity, 11.1 meters per second. And this works out to 43.5 meters, or about 145 feet. So, if you throw an object at 80 kilometers per hour at a 60-degree angle from the horizontal of the Earth, it will go out a distance of about 145 feet. And of course here what we're doing is we're neglecting air friction, drag due to the air molecules on the object. Of course, in the real world, if you take, say, like a baseball and you throw it, there is some air friction. As that object is going through the air, it tends to slow the object down. So rather than going out 145 feet, it'll fall a little bit short. But if your object is spherical and fairly heavy and not too big, the error here will be very, very minimal. And the important thing to remember too, this is independent of the weight and the mass of the object. Every object that's thrown at that velocity, at that angle, will hit the same spot. It does not matter how dense or how much that object weighs. Now, there's some people out there that think gravity doesn't solve this, that there's no such thing. Well, I'd like to see you solve the problem using buoyancy and density. I'd like to see someone solve a trajectory problem, a ballistic flight problem using buoyancy and density. Can't be done. And if you want to test this out, you go ahead and try it yourself, and you'll see that your object will go out about that far, and it'll reach a height of about 63 feet or 18.9 meters. Now, in the next module, we're going to get into the Coriolis effect. Now we have all our definitions, we have all the ammunition we need to talk about and describe the Coriolis force and the Coriolis